Have you ever looked up at the night sky? You might see the moon, you might see a few planets, or thousands of twinkling stars. It all seems so quiet, so peaceful. But that quiet is an illusion. Space is not empty. It is not silent. Right now, at this very moment, something is raining down on you from the heavens. It is invisible. You cannot feel it. You cannot hear it. But it is there, passing through your body, through this building, and through the very ground beneath your feet. This strange, unseen rain is a constant stream of particles from the depths of the universe. They are the universe's secret messengers, carrying tales of cosmic violence and unimaginable energy. This cosmic shower is not like the rain you know. It doesn't come from clouds in our sky. It comes from places so far away that it's hard to imagine. Some of these particles started their journey millions or even billions of years ago. They have traveled across vast, empty stretches of space. They have dodged black holes and sailed through giant clouds of gas. They have been flung from exploding stars and accelerated by mysterious cosmic engines. The story of cosmic rays begins over 100 years ago. In the early 1900s, scientists were puzzled by a strange phenomenon. They used sensitive instruments called electroscopes to measure electric charge. They noticed that no matter how well they insulated their electroscopes, they would always slowly lose their charge. His name was Victor Hess, an Austrian physicist. In 1912, he decided to take his electroscopes up where no one had taken them before, high into the atmosphere in a hydrogen balloon. He made several flights day and night, ascending to altitudes of over 5 kilometers. He confirmed what others had hinted at. The radiation did not decrease. In fact, it grew stronger the higher he went. So, what are these cosmic rays? Let's get one thing straight. They are not really rays at all. That name is a historical accident, a leftover from when we first discovered them. The truth is much more interesting. Cosmic rays are tiny bits of matter. They are particles. Most of them are protons, which are the hearts of hydrogen atoms, the most common element in the universe. But they can also be the nuclei of heavier atoms, like helium, carbon, or even iron. Imagine stripping an atom of all its electrons, leaving just the dense, positively charged center. That's a cosmic ray. The thing that makes cosmic rays so special is their incredible speed. They are traveling at nearly the speed of light. A single tiny proton traveling as a cosmic ray can carry the same kinetic energy as a baseball thrown at 100 kilometers per hour. All that power concentrated into a particle that is trillions of times smaller than the baseball. So where do these tiny, super-fast particles actually come from? The source of a cosmic ray has to be something truly powerful. Think of it as a cosmic particle accelerator, a natural machine far grander than anything we could build on Earth. We're talking about places where stars die in spectacular explosions, or where matter is torn apart by the gravitational pull of a black hole. These events create the perfect conditions for accelerating particles. They generate massive shock waves and tangled magnetic fields. A slow-moving particle that wanders into one of these zones can get trapped. It gets bounced back and forth across a shock wave, gaining a little more speed and a little more energy with every single bounce, like a cosmic pinball, until it's finally kicked out at nearly the speed of light. Most of the cosmic rays that bombard the Earth are thought to come from within our own galaxy, the Milky Way. The prime suspects for their creation are supernova remnants. These are the expanding clouds of gas and debris left over after a massive star has exploded. But some cosmic rays come from much, much farther away. The most energetic ones, the particles that carry the power of a baseball pitch, are simply too powerful to have been made in our galaxy. They must be extragalactic, meaning they originate from outside the Milky Way. They are messengers from distant galaxies. After traveling for millions of years across the galaxy, a cosmic ray finally approaches our solar system. Its long journey is almost over, but it faces one final formidable obstacle: the Earth itself. Our planet is not a defenseless target floating in space. It is protected by a powerful, invisible force field called the magnetosphere. Generated by the swirling liquid iron in the Earth's core, this magnetic field extends tens of thousands of kilometers out into space. It acts as a giant shield, deflecting the constant stream of charged particles from the sun, known as the solar wind, and protecting us from the worst of the galactic cosmic ray bombardment. When a cosmic ray, which is a charged particle, enters this magnetic field, it is forced to change its direction. The magnetosphere is strongest near the equator and weakest near the poles. The magnetic field lines curve downwards at the north and south poles, creating two funnels. These polar cusps act as gateways, channeling incoming charged particles directly towards the upper atmosphere. This is why the beautiful auroras, the northern and southern lights, are seen near the poles. This magnetic shield is absolutely crucial for life on Earth. Without it, the full, unfiltered blast of cosmic rays and solar particles would bombard the surface. What happens when a cosmic ray successfully navigates the galaxy, bypasses our magnetic shield, and finally reaches our planet? The original particle, which scientists call a primary cosmic ray, almost never completes the journey to the surface. Instead, it slams into the nucleus of an atom in the upper atmosphere. This initial collision is incredibly violent. The immense energy of the primary cosmic ray is unleashed in a cataclysmic explosion, shattering the atmospheric atom and creating a spray of brand new particles. This is just the beginning of a chain reaction. The new particles created in that first collision are themselves highly energetic. They fly off in different directions, only to collide with other atmospheric atoms a fraction of a second later. The result is a cascading, multiplying effect. One single primary cosmic ray can trigger a vast avalanche of billions of secondary particles that shower down through the atmosphere. This shower of secondary particles spreads out as it travels downwards, sometimes covering an area of several square kilometers by the time it reaches sea level. It is this secondary shower, not the original primary particle, that we experience on the ground. You are being rained on by the grandchildren of a particle from an exploding star. Every second, several hundred of these secondary cosmic ray particles are passing harmlessly through your body. The most persistent of these are the muons. Muons are like heavy, unstable cousins of the electron. They can travel through hundreds of meters of solid rock. This is why cosmic ray detectors are often built deep underground in mines or tunnels. The interaction of cosmic rays with our atmosphere does more than just create a shower of secondary particles. It also leaves behind a permanent radioactive signature. One of the most important creations of cosmic rays is an isotope called carbon-14. When cosmic rays smash into atmospheric atoms, they release a spray of neutrons. When one of these slow-moving neutrons is absorbed by a nitrogen-14 atom, it can knock out a proton, transforming the nitrogen into carbon-14. This new atom is radioactive, with a half-life of about 5,730 years. This cosmic ray-produced carbon-14 mixes throughout the atmosphere and is absorbed by all living things. But the moment it dies, it stops taking in new carbon. The carbon-14 within its remains begins to decay at a predictable rate. By measuring how much carbon-14 is left in an ancient piece of wood, bone, or cloth, scientists can determine its age with remarkable accuracy. This technique, known as radiocarbon dating, is all thanks to cosmic rays. Cosmic rays are therefore a fundamental tool for archaeologists, paleontologists, and climate scientists. They have allowed us to date ancient human settlements, understand the timeline of animal extinctions. Cosmic rays are not just a scientific curiosity, they have a real and sometimes disruptive impact on our modern technology-dependent lives. This is especially true for the sensitive electronics that power our world. The microchips at the heart of our computers, smartphones, and servers are built on an incredibly small scale. When a high-energy particle from a cosmic ray shower, like a neutron or a muon, strikes one of these microscopic circuits, it can cause a tiny bit of chaos. This is known as a single event upset, or SEU. An SEU occurs when a particle deposits enough energy in a memory cell to flip a bit from a 0 to a 1 or vice versa. This may sound small, but it can have significant consequences. It could cause a minor glitch in your laptop, a pixel on your screen to flash the wrong color. However, for critical systems like aviation electronics, medical equipment, or large-scale data centers, even a single bit flip can be a serious problem. Engineers who design these critical systems are very aware of this invisible threat from space. They have to design electronics that are radiation hardened. Another is to use redundancy, such as triple modular redundancy, where three identical circuits perform the same calculation simultaneously. If a cosmic ray hits one circuit and causes an error, the other two can outvote the faulty one. While cosmic rays pose a background risk to technology on the ground, they are a much more serious concern for astronauts in space. Here on Earth, we are protected by two powerful shields, the planet's magnetic field and its thick atmosphere. Astronauts in orbit, however, are above most of the atmospheric shield. Those on the International Space Station are still largely within the protection of the magnetosphere. For explorers traveling beyond this magnetic shield, on missions to the Moon or Mars, the danger is far greater. Without this protection, astronauts are exposed to the full, unfiltered blast of galactic cosmic rays. These particles, especially the heavy nuclei like iron, are like microscopic cannonballs. When these heavy particles pass through human tissue, they can damage cells and break strands of DNA. This damage increases the long-term risk of developing cancer, cataracts, and potentially degenerative diseases of the central nervous system. The constant bombardment is one of the single biggest health challenges facing long-duration spaceflight. Protecting astronauts from this threat is incredibly difficult. Building a spacecraft with walls thick enough to stop high-energy galactic cosmic rays is not practical. Even inside the spacecraft, astronauts see direct evidence of this cosmic bombardment. When they close their eyes to sleep, they often report seeing strange flashes of light. These are thought to be caused by cosmic rays passing directly through their eyeballs. Managing this constant exposure is a top priority for NASA and other space agencies. Before we can safely send humans on the long journey to Mars and beyond, we must find better ways to shield our explorers from the relentless hail of space's bullets. Since cosmic rays are invisible particles that arrive from random directions, studying them requires some truly clever and often enormous detectors. We cannot simply point a telescope and take a picture. Instead, scientists have become masters of catching the ghostly footprints these particles leave behind. One of the most common methods is to study the extensive air showers they create. When a primary cosmic ray hits the upper atmosphere, it creates a cascade of billions of secondary particles. To see this shower, scientists build vast arrays of detectors spread out over many square kilometers on the ground. One type of detector is a water tank. When a particle from the air shower passes through the water faster than the speed of light in water, it produces a faint cone of blue light called Cherenkov radiation. The Pierre Auger Observatory in Argentina is a prime example, covering an area of 3,000 square kilometers. Another ingenious method is to look for the faint ultraviolet light that the air shower itself produces. As the cascade of particles excites nitrogen molecules in the atmosphere, those molecules emit a subtle fluorescent glow. For the most elusive particles, scientists go deep underground. To study muons and the mysterious particles called neutrinos, physicists build detectors in mines, tunnels, or even under the ice of Antarctica. The Ice Cube Neutrino Observatory, for example, uses a cubic kilometer of Antarctic ice as its detector, instrumented with thousands of light sensors. We have a pretty good picture for where most cosmic rays come from. The sun makes the low-energy ones, and supernovas in our galaxy make the medium-energy ones. But then, there are the monsters. Scientists have detected a handful of cosmic rays with energies that are simply off the charts. These are the ultra-high-energy cosmic rays, or UHCRs. A single one of these subatomic particles can carry the kinetic energy of a professionally thrown cricket ball. The problem is that nothing in our galaxy seems powerful enough to create them. A regular supernova just doesn't have enough juice. These particles must come from somewhere else, from the most extreme and violent environments in the entire universe. The mystery deepens because of a cosmic speed limit. The universe is filled with a faint glow of microwave radiation left over from the Big Bang. A particle with as much energy as a UHCR should not be able to travel very far before it collides with these microwave photons and loses its energy. This puts a limit on how far away their source can be. Yet, when we look in the direction they came from, we don't see any obvious candidates. The oh my god particles remain one of the biggest unsolved puzzles in astrophysics. Why do we invest so much time, effort, and money into chasing these invisible particles? The quest to understand cosmic rays is more than just an academic exercise. These particles are direct samples of matter from the most extreme environments in the cosmos. By studying them, we are performing a kind of cosmic archaeology, using these ancient relics to learn about the violent processes that shape galaxies and drive the evolution of the universe itself. The pursuit of cosmic rays has consistently pushed the boundaries of both physics and technology. In the early 20th century, they were our only window into the subatomic world, leading to the discovery of antimatter and a whole zoo of new particles. This laid the groundwork for the Standard Model of particle physics, our current best description of the fundamental forces and building blocks of nature. Today, the mystery of the highest energy cosmic rays continues to challenge our theories. If their origin involves new physics beyond the Standard Model, their discovery could trigger the next great revolution in our understanding of reality. Furthermore, understanding cosmic rays has very practical implications for our future as a spacefaring species. As we plan for long-duration missions to the Moon, Mars, and beyond, cosmic radiation remains one of the most significant health risks for astronauts. By studying the composition and energy of these particles, we can better design the shielding, spacecraft, and habitats needed to protect our explorers. Ultimately, the search for the origin of cosmic rays speaks to a fundamental human drive, the desire to explore and understand. We look up at the sky and wonder not just what is out there, but how it works. Our journey through the world of cosmic rays has taken us from the highest reaches of our atmosphere to the most violent corners of the universe. We began with a simple puzzle, a mysterious radiation coming from space. Over a century of investigation has revealed that this radiation is not a ray at all, but a relentless shower of high-speed particles. These are the atomic hearts of distant stars, launched on epic journeys across the galaxy by cataclysmic explosions. Every moment of every day, these tiny bullets from space rain down upon us, passing through our bodies and our world, connecting us physically to the cosmos. We have learned so much about these invisible travelers. We know that most of them are born in the fiery remnants of supernovas, accelerated to nearly the speed of light by expanding shockwaves. We have seen how our planet's magnetic field acts as a vital shield, protecting us from the worst of this bombardment. Yet for all we have learned, the mystery of cosmic rays is far from solved. The existence of the ultra-high energy oh my god particles continues to defy our neatest theories. These particles are so powerful that their origin points to physics and astrophysics that we do not yet understand. They are a stark reminder that the universe is still full of surprises, holding secrets that challenge the very limits of our knowledge. The puzzle that Victor Hess began to unravel in his balloon over 100 years ago continues to captivate and challenge scientists today, promising new revelations about the fundamental nature of our universe. This enduring mystery is part of what makes cosmic rays so fascinating. They represent a direct, tangible link between our lives on this small blue planet and the immense, chaotic, and beautiful universe that surrounds us. They are not just an abstract concept for physicists. They affect our technology. They pose challenges for our future in space, and they are woven into the very history of our planet. Studying them is not just about understanding distant astronomical events. It is about understanding a fundamental aspect of our own environment. The invisible rain from space is a constant reminder that we are not separate from the cosmos, but an integral part of its grand, ongoing story.